gravitational wave experiments. First, in connection with probably the best cryogenic resonance detector ever built, Auriga, at the INFN labs in Legnaro near Padua, and later with the design of LISA, and in particular the responsibility of the Pathfinder project, aimed at testing all the critical, highly sophisticated technologies that are at the core of a spaceborne optical interferometer. In terms of the residual acceleration between the test masses, that is the most comprehensive figure of merit, correct me if I'm wrong, Stefano, for such an experiment.
There.
The LISA Pathfinder performance was better than the design target by an average factor exceeding 5, showing the real possibility of having an instrument covering the full band between 5×10⁻⁴ and 1 Hertz. Besides this, I should say that Stefan is an extremely brilliant lecturer, one of the best I ever listened to, as you will see by yourselves after all. So again, thank you so much for being here, Stefano. Incidentally, Naples is your homeland in a sense. On behalf of everybody here, and enjoy your talk.
I want to add that Stefano is another SIGGRAPH medalist. He got the SIGGRAPH medal in 2018, so please.
Excellent.
Thank you very much, guys. Thank you for this kind invitation. I hope, in a sense, it didn't raise your expectation too much. This is a talk on LISA, as you may have guessed from the title, that you may know is a project to fly a sort of spaceborne Ligo, so test masses and laser interferometer, just a factor 1,000 bigger, that right, million kilometers instead of kilometers, sorry, factor million bigger, that ESA, the European Space Agency, together with its member state and NASA, are pursuing since many years now. The aim of the detector is to cover a frequency range between a few tenths of microhertz. I pointed you to the inverse of a day, so waves that oscillate over a good fraction of the day to some fraction of a hertz. This is a frequency range that ground-based detectors have no realistic chance of exploring because of the gravitational noise due to the motion of the Earth's surface and the atmosphere. So a very fundamental noise. So I debated very much with myself, where should I start with this talk and let me start on why we do that. Why you want a gravitational wave detector acting at this very low frequency? Well, the explanation, it's readily understood if you consider that most of the source of gravitational waves, I give for granted that you know everything about gravitational waves by now, after all these brilliant lectures. So most of the sources of gravitational wave are binary bodies spinning one around the other. And the frequency of the wave is twice the frequency of the spinning, is twice the frequency of revolution. And with pretty high accuracy, the frequency of revolution is given by Kepler formula. So it only depends on the mass of the two bodies and their separation. Innocenzo, do you see everything? Is that fine?
Everything is excellent.
Okay. So the Kepler formula depends on the mass and the separation of the two bodies, right? And now I'm sure you know by now that the separation between two bodies cannot get smaller than a magic number that Einstein discovered, which is the sum of the two Schwarzschild radii, which is just a combination of the mass and some fundamental constant. If you take two ordinary bodies, they would collide much before having this small distance. But even if you take two black holes, if they get closer than this distance, they would merge in a single black hole and end any radiation. So if you express the separation normalized to this minimal distance, so in a sense you have a separation measuring the distance from the final collapse, then the frequency of the gravitational wave becomes a decreasing function of the mass and a decreasing function of the separation. And this is a contour plot of this function. So you immediately get what you achieve by punching through this wall of the terrestrial gravity noise. On one side, because you have now low frequency, you access sources that are made by bodies that are much, much more massive than the body that emits the radiation for LIGO and Virgo. So we are talking here 1 million times the mass of the sun. This is the realm of supermassive black hole in all their incarnation, and I'll tell you a little bit about this supermassive black hole. So this is a Nobel Prize winning cartoon. It's an animation of the motion that is now pretty old, but it's an animation of the motion of the stars around the center of the Milky Way, of our galaxy. And so you see the stars rotating with period of the order of the period of rotation of Jupiter around something you cannot see. If you calculate the mass of that object, this is a supermassive black hole, a few million times the solar mass. So you cannot see, so very likely a black hole. And now we see galaxies interacting. This is an animation from the Hubble Space Institute, which is connecting a snapshot of the deep field of Hubble showing interacting galaxies. So when you see two galaxies interacting, in reality what you're seeing is the formation of a binary of supermassive black hole. The two supermassive black holes in the center of those galaxies are forming a binary that is spinning and spinning like the black holes of LIGO, but these are much bigger. And because the gravitational wave signal scales with the product of the masses, this is by far the most intense gravitational signal you can think of. And the plot you see here, this plot here is a simulation, oops, it's very slow, is a simulation of LISA data with no filter, just the filter you need to downlink the data to the ground, right? And so you see the signal to noise ratio. This is not particularly intense, but the signal to noise ratio of these signals is enormous. The consequence of that is that these things are visible. Basically, we used to say everywhere in the universe. So this is a plot of the signal to noise ratio versus the mass of the black holes and the redshift of the luminosity distance. And a redshift of 20 is before recombination, and you see that two of these guys would have a signal to noise ratio in some mass range in excess of 100, even if they are at the edge of the universe. And so to give you a little flavor of what the people think that they will be able to do with this instrument, and this is all LISA, right, is that because these supermassive black holes spin down, like the black holes of LIGO, right? They start orbiting with a 1 day period, and then they go faster and faster and faster. And after a year or a month, sooner or later, they enter in the LISA sensitivity band. And so the people hope to make a sort of stratigraphy of the universe, where you see the tree of formation of the galaxies nearby us by successive merger of the black holes in the center of those galaxies, where two galaxies become a bigger galaxies and the two black holes in the center merge into a single black hole. So really a sort of stratigraphy applied to black holes. And obviously the secret dream is to understand where those black holes are formed and how they are formed. To give you another little taster of the physics of supermassive black hole, oh no, okay, that I can skip, I think. So another little taster of the physics of the supermassive black hole is when one small black hole or a neutron star, a compact object, start orbiting one of these big black holes. And there are plenty of those in the galaxies, right? The orbit, this is a realistic simulation, but it's slowed down, what you see there, the movie. You see the orbit is very non-Keplerian. Maybe you remember that Kepler says the orbit are plane. These are not plane. And so what the guy does is a sort of a map of the gravitational field around the black hole. This is an animation with sound. I hope you can hear the sound. So the orbit becomes faster and faster and faster and faster I transform the gravitational wave in a sound, and then, pack, the guy falls into the event horizon of the central body and is gone, because nothing can get out of the event horizon of the central body. So this will be the most striking demonstration of the existence of the event horizon. And there is a lot of physics you can do. By the way, you would be curious to know that recently XMM Newton has detected, which is an X-ray observatory, has detected this pulse of X-ray emitted with a period of a few hours that some people think is the crossing of a small object of the accretion disk of the black hole by a small object. So this could be one of these extreme mass ratio in spiral information. So you measure everything of this phenomenon, the spin, the mass, the quadrupole moment. And so you can demonstrate this famous no-hair theorem with very high precision that black hole is just mass spin. Black holes do not, the body falling in the black hole cannot distort the surface of the black hole, while if it is another body, it would be distorted by the gravitational field. And you measure this thing to such a high precision that you should be able to discriminate if the phenomenon doesn't look like something orbiting a Kerr black hole. You should be able to say if it is a big environmental perturbation around the black hole or some exotic object. The black hole is not a black hole, it's a collection of bosons. So there are many, many theories on that. But the important thing is that the signal discriminate among those hypotheses. And so a very powerful fundamental physics laboratory. The other, that I think you have seen, I think Bernard that told you a little bit about this. You know that gravitational wave give you the luminosity distance to the source. That's because from the rate at which the source spin up, you can calculate how much is the energy emitted by the source. And by measuring how much energy you collect here, you can scale the distance. Now, the interesting thing is that LISA will detect the luminosity distance of many categories of this object, this extreme mass ratio spiral, but also the supermassive black hole at different redshift, and so should be able to give you the equation of state of the universe independently of any other method, with a completely independent method on a large span of redshift, which is something that very few instruments can do. Now let me give you the opposite side of this plot. We have seen the plot for the big masses, but now let's see what happens at big separation, when the separation between the two bodies that are orbiting are much, much larger than the sum of the two Schwarzschild radii. So that means the two bodies are very far away in time from the final collapse. So these are non-transient sources. This is regular, dignified astronomy as the old astronomer knew it, where you observe a source for a long time and it does not collapse into nothing, right? And the abundance of sources here is breathtaking. Basically, LISA would be an impressive observatory of the binary or compact object in our galaxies. I'll tell you in a second. And on the edge of this zone here, we will also see, LISA will also see, because I will probably not be there, we'll also see transit, the final phase of the spinning of the LIGO black hole, and I'll tell you in a second of that. So let me tell you about the compact object in our galaxies. People calculate that LISA will be able to discriminate tens of thousands of this object. You heard correctly, tens of thousands, 10 to the 4, right? These are binary or white dwarfs, right? They are very, very abundant in the galaxy. For some of those, we know everything because we observe in the optics, so we can calculate the gravitational wave signal that LISA will see. And in the old days, before the detection of gravitational wave by LIGO, this chart here was our winning chart. when we turn on LISA, we have a guaranteed signal. If the signal is not there, that means that LISA is broken, right? So there are no chances. We know everything about those sources. We can calculate the signal. Now LISA will take data for years. And so by integrating these signals for years, we'll have a frequency resolution of 1 over a year or more, so microhertz. And so the people already calculate that you should be able to discriminate in frequency the signals of many of those ones, and that's what add up to the 10,000 sources. For comparison, this is one of the map, is a simulated map of the universe of those binaries as seen by LISA, compared with a similar map done by Gaia on the visible part of this this object. So you may say this will be the most impressive survey of non-visible object in the galaxy. At the edge of this, they are so abundant that even that there are so many that some you will not discriminate, and so the people expect a foreground to be, which is in a sense a limitation for the detection of other sources. Now let me, I'm running too fast because I never prepared a 2-hour talk, so you had to be indulgent to me. So this view graph that you're not supposed to read, I just told to one of my young colleagues who gave the presentation what you can do with this survey of galactic binaries, right? Read the titles, the shape of the Milky Way components, the structural parameter, awaken the satellites of the Milky Way. So the people think that the data of LISA will give years and years of study about the composition of the galaxies, of our galaxy, of the Milky Way. What amazes me really most is that the people think that from those signals we should be able to detect planets orbiting those binary or compact objects. So this binary or white dwarf will have planets, and the perturbation on the orbit of the compact object of the binary due to the planet will be visible, will let a fingerprint in the gravitational wave. That I find really amazing. I was rushing to this, which is, you know, that Ligo has made a Ligo and Virgo and made us so happy because in 2015 they finally detect a black hole binary. Now, a few months after the paper with the detection, Alberto Cesana first, and then a lot of other people calculated that if LISA would have been up 10 years before the event, so in 2005, LISA would have detected the signal from that same black hole when it was still very much separated, and so with a period of 100 seconds. So the two black holes, instead of spinning at a fraction of a second, there have been years where they were spinning with 100-second periods, accelerating. At some point, they disappear from the LISA band, and after a week or so, they reappear in the LIGO band. And the people calculate that if you can follow one of these sources throughout the two bands of two detectors, so on so many decades of frequency, you can do an exceptional improvement in, for instance, the measurement of the parameters of the source, and so the fundamental physics. So for instance, this is some parameter, don't ask me what this parameter, as measured only with LISA, and this is measured by LISA plus ET. You see, it's a few orders of magnitude improvement in the measurement of all the fundamental parameter of the source. And so that's why the people start to show this, to show this view graph where you see the same signals detected by more than one detector with an incredible increase of the science you can do. And that's called multi-band gravitational wave astronomy. You just need to start as science, then you discover you can do incredible things. Okay, so now I'll leave science, and with much to my relief, because I'm a plumber, a mechanician, right? And I'll tell you about the instrument. Now, sorry, I keep forgetting things, but that's worth mentioning. you must realize that the data of LISA, it's a mess. There are so many signals that the data stream from a detector like LISA is entirely dominated by signals. Noise is almost undetectable, right? So the problem is, will we be able to discriminate among all those signals? Will we be able to make a map of the sky separating 2 or 3 or 4 supermassive black hole mergers from the galactic foreground, plus the binary from the galactic, and so on? The answer is yes. The people have been studying this problem for years. The point of attack here, the approach here, is that some group produces synthetic LISA data with our model of the noise, plus a model of the universe and all possible sources. They distribute those data blind, and you may subscribe to this exercise. You get the data, and you test your method of data extraction to see if you reconstruct accurately the map of the sky. Obviously, the result of this exercise that is continuing, becoming more and more realistic, is that the most bright sources are always detected by everybody with good accuracy of the parameters. And as soon as you go to the smallest and smallest and smallest signals, ambiguity increases and the problem becomes most difficult. But we have learned to do a lot on this. And if you're curious, you have a link there. Just join. This is open. You join the LISA consortium. Join this, and you can participate to the mock LISA Data Challenge. Actually, mock is not part of the name anymore. They are called LISA Data Challenge. Okay, now let me talk of the instrument, which is my job, right? It's the detector. So this is a view graph taken from another presentation I did a few days ago. But the message of this view graph is that when you're in space, you should not think so much to an interferometer where you send the light back and forth many times between two mirrors. You should much more think on what the people do to locate the position of a satellite in space, right? The satellite sends a microwave to the ground station, and you measure the frequency of the received wave, and if the spacecraft moves, recede from you or moves toward you, you see the frequency of the transmitted wave being changed. This is the famous Doppler effect. Now, if you calculate in general relativity, you have a shift. If there is a passing by gravitational wave, you get a shift, even if the spacecraft and the antenna keep their coordinates, like this cartoon wants to represent, and the time derivative of the relative frequency shift of the laser beam or the radio beam you're sending from one spacecraft to the other one is directly proportional to the curvature tensor transported by the wave. It's also obviously proportional to the separation of two objects, which is the reason why we have a 1,000,000-kilometer detector. If you want to, to be less vague, so the basic measurement element in a device like LISA is a satellite here that I call the emitter, sending a laser beam, but you could do with microwave. It would not be sensitive enough, but in principle you could do, to a second spacecraft, which is a receiver, that measure the frequency of the received beam, right? Now, if you calculate, if you're more familiar after all this lecture with the metric tensor, general relativity tells you that even if the frequency of this is fixed and non-fluctuating, the frequency received here is shifted relative to the frequency at the emission by a quantity which is proportional to the difference of the metric tensor at the two places. Even more important, this frequency shift is oscillating. I hope you can see in my cartoon that the color is changing, right? The frequency shift is oscillating at the frequency of the gravitational wave. And actually, as I said in my previous view graph, it is the time derivative of the frequency, which is in reality proportional to the more significant, physically significant signal, which is curvature, right? So your physical information about the gravitational wave is in this quantity here, a time-varying frequency shift in the received beam. That's the trick. That's all. Now, unfortunately, as you may know, there is a much more mundane way to do a frequency shift in an arrangement like this one, which is exactly to move either the source or the receiver, right? Then by ordinary Doppler effect, if you accelerate the source, for instance, like in this cartoon here, the receiver will see the frequency going from blue to red, according if the source is receding or is accelerating toward you. And so it's not surprising that if you calculate now, obviously these are all small effects, they add up, your time derivative of the frequency shift is proportional to the gravitational wave signal, but it's also proportional to the difference of the acceleration of the two satellites relative to the local inertial frame along the line of sight, along the line of the beam, right? And there is no way you can distinguish between the two by a local measure. And unfortunately, very early in the history of LISA, we realized that if you put a spacecraft in an orbit around here, right, at the same distance from the sun as the Earth is, the solar radiation pressure of the sun, which is not constant because the power emitted by the sun is fluctuating and is fluctuating at microhertz, at the millihertz, and even at hertz, right, would shake those spacecraft so much that the Doppler effect, the signal due to the Doppler effect would cover any interesting astrophysical signal. So this was, you know, a little head scratching, how we cope with that. These spacecraft are too noisy to do any significant gravitational wave measurement. And so the idea that came out was, okay, let's carry an inertial reference inside the spacecraft. So let's carry a test mass, a body, which is isolated, is free floating inside the spacecraft like an astronaut, right, in the space station. It is now inside the spacecraft, so the solar radiation pressure does not hit this reference body, so it flies quietly and with no acceleration. Obviously, you should not touch it. And so the spacecraft cannot contact the test mass, and that means that the spacecraft has to do something to avoid collision between the spacecraft and the test mass. And this problem is solved by measuring where the test mass is inside the spacecraft, and instead of pushing the test mass to stay at a fixed position in the spacecraft, feed back this information to a set of thrusters, rockets, little rockets that push the spacecraft and keep it centered on the test mass so that you avoid collision. So now the test mass is flying unaffected by the solar radiation pressure, so perfectly clean with no acceleration, at least hopefully to some limit, and I'll come back to that limit because it's important. The spacecraft will be noisy, but now you can measure the acceleration of the spacecraft relative to the test mass, and it's an easy calculation that if you measure the acceleration of the spacecraft relative to the test mass, right, by measuring with an interferometer the relative acceleration, right, on both test masses, then you measure the Doppler shift between the two spacecraft, which is a combination of their acceleration and the gravitational wave signal. Then you can do this plus this minus this. Let's see if I remember correctly. You do this plus this minus this, and the acceleration of the spacecraft cancel out. And it's like you had sent this laser beam directly from one test mass, which is now protected from the sun, to another test mass, which is also protected from the sun. So you will have some acceleration because you're not exactly good at canceling all the disturbance forces, but those acceleration are much less than the acceleration due to the spacecraft. Those residual acceleration is the subject of basically the second half of my talk, or even the remaining two-thirds. So they are very important, but they are small. They are much smaller than what you would get if you try to track just two free-falling spacecraft around the Earth or around the sun. at the same distance. If you want to, so you must realize that you cannot send the light back and forth between two spacecraft at 1 million kilometer, at 2 million kilometer distance. If you send the light from this spacecraft to this one and reflect it back on a mirror, even if you send 2 watts, by the time the light comes back, it's a few photons per second, and you don't do any interferometer. So in reality, LISA consists of 6 beams that propagate from one test mass to the other one, all right? 1, 2, 1, 2, 1, 2, organized in 3 arms. And you have to extract gravitational wave by combining the signal from these links. Each links provide a frequency measurement at this side, right? And by combining those frequency and their variation, you have to get the gravitational waves. And I'll try to guide you across how we get that. Okay. Before we move, let me tell you that we don't have only 2 spacecraft. We have 3 spacecraft. Says everything has been slowed down very much. Let's see if it starts again. Or okay, I hope you can see. Innocenzo, do you see LISA rotating around the sun?
Yes, initially there was a lag, but now it goes beautifully. Okay.
So LISA is not just 2 pairs of the spacecraft with their test mass, is 3 spacecraft, right, at 2.5 million kilometers away. Now it turns that there is a miracle in celestial mechanics where you can put 3 spacecraft in 3 orbits very similar to the orbit of the Earth. They have perfectly tuned small eccentricity and small inclination, and they form a triangle that virtually goes forever around the sun with no need to do maneuver. Huh? This is not kept together by some rocket. It's just celestial mechanics. This turns out it's not exact. There are residual velocities, and the formation is stable for 10 years. Then the perturbation due to the other bodies disrupted. And it's very important to have the observatory going around the sun, because this forms a sort of synthetic aperture telescope that allows you to triangle the source and to get the location of the source in the sky for the brightest source with less than an arc-minute precision. If you want to give a closer look to the LISA instrument, and you tell me, Innocenzo, when you think it would be better to make a break, but otherwise I continue. So if you want to see the instrument, the basic instrument is this set here, right? A spacecraft receiving a beam and controlling its own acceleration using its own test mass, right? And the instrument is this device here. And if you give a closer look, it's made of 3 elements, basically. A test mass, that's the reference test mass, is surrounded by a lot of accessories that we call the gravity reference sensor. I will show you a little bit. It's used as a reference for the drag-free and as an inertial reference to correct the signal. An optical bench where everything, all the optics is sitting on this optical bench, including the local interferometer that measure the acceleration of the spacecraft relative to the test mass, and the interferometer that measure the acceleration or the gravitational wave signal by sending and receiving the light from a distant spacecraft. This telescope here is not to look at a star. Huh? This is a telescope to receive, to collect the light from the distant spacecraft and to send the light to the distant spacecraft. Okay, and so the third element is the telescope. So the test mass in flight is this is a 2 inches test mass where we are in Europe. It's a 5 centimeter test mass. It's gold platinum. The reason why I can show you is that because we flew 2 of those on LISA Pathfinder. I'll tell you in a short while. And so in flight, this cube here fits into this hole here with no contact. Huh? There is no, it floats with millimeters gap all around. 3 to 4 millimeters gap, depending on the distance. However, it's surrounded by electrodes. You see this bright surface here are electrodes, right? And these electrodes are needed because in reality, we follow the test mass only in the direction along which we do the gravitational wave measurement. In all other directions, we have to push very gently the test mass to follow the spacecraft, because we have two test masses in one spacecraft and we cannot follow them in all directions, right? So we apply little forces. They are 90 degrees with the measurement. So in principle, to zero order, they don't disturb. To first order, they will be some sorts of disturbance, right? And there are more accessory, I'll tell you in a while. The optical bench. The optical bench is very complex. There are many interferometers on the same optical bench. It's a piece of zero dur, 30 centimeter. This is not the optical bench, but it's just a test one where Glasgow is practicing assembling components. I'll tell you a little bit more about the technology to assemble this optical bench. What I want to tell you here is that this piece, 30 centimeter wide, is the equivalent of one of the end room of Ligo, right? All the interferometer of LISA is on this piece of glass, right? Except for the telescope that you may assimilate to the entry point of the vacuum tube. So this is a pretty packed device. Both sides of this disk are used to accommodate device, and it's certainly a pretty sophisticated piece of equipment. If you want to see the two things coming together now during the current stage of development of LISA, this is taken from one of the studies in the consortium, but I have an old rendering that I hope runs that shows the light coming through the telescope being distributed on the optical bench to do the interferometer, the satellite-to-satellite interferometry, and one little beam going down across a sort of Russian doll system and hitting the test mass, right? So that's how LISA looks, and to be clear, this is of the order of a meter, 35 centimeter or so, right? So it's a pretty small device compared to LIGO or VII. Okay, there are complications relative to LIGO. One is frequency noise. I don't know how much Giovanni told you about the working of this interferometer, but you must know that lasers are miserable sources of light. LISA, which is much less demanding than LIGO, requires to detect frequency shift. If you convert gravitational wave into frequency shift, we are talking microhertz. This is noise, so it's microhertz per root hertz, but it's basically microhertz. And if you take the most stabilized laser at the frequency of LISA, the stability is kilohertz. So there are 9 orders of magnitude difference. So how you do that? If you have to measure such as a tiny frequency shift, and the frequency of your laser source is oscillating, is fluctuating by billion times what you have to measure. Well, the classical trick invented by Michelson is, well, you want to compare the light that has propagated different path. Just use the light that has been generated at the same time, right? So if you do two paths that have exactly the same length, whatever is the light that comes to the beam splitter, it goes in this side and this side as the same frequency. So when you recombine them, if you see a frequency difference or a phase difference, it's because of something that has happened here or in both places, right? And Michelson, you remember, was successful in operating with a flame, right? He didn't have a laser. He didn't have even a light bulb. He had a flame and could do interferometry with a flame because the light you are comparing is the light that has been generated at the same time and so has exactly the same phase. Now, the arm of LISA, I say they are equal. They are not equal at all. They differ by 100,000 kilometers, so a good fraction of a second, right, in propagation time. And they change by 10,000 kilometers over a year. So no way you can do. And the people, however, has realized that combining those signals from those 6 links in time, so you can take the signal that has been propagated from this satellite to this satellite, add the signal that has been sent from this satellite to this satellite, then you cancel the noise of the laser here. And if you're smart enough to combine signals that have been delayed, that have the proper delay, at the end you synthesize, you compare two beams that have traveled exactly the same path, has been emitted exactly by the same source at the same time, and so you cancel the frequency noise. This is called time-delayed interferometry. It's a rather sophisticated technique. It requires it, and it achieves a suppression of the laser noise in software, going from just a one-arm comparison. You could do some improvement by doing round trip or doing Michelson, but what you need is a final improvement of 6 orders of magnitude to cancel the frequency noise of the laser. And this requires very good phase measurement. You have to measure phase with very high fidelity because you have to subtract two very noisy signals and look at the difference, which is 1 part per billion of the dynamic range of the two signals. This has been achieved in many labs now. This is the last one from my colleagues in Hanover. They mix three beating signals between 3 interferometers, and the sum of the 3 signals must be 0 if you do the phase, if you measure the phase correctly. And so you see on the left scale, you see the fluctuation of the phase of the 3 interferometer is 10 to the 12 microcycle, and the combination of the 3 interferometer is this brown line here that you have to read to the right scale, which is 100 instead of 10 to the 12. So you realize that the suppression of the phase is pretty good. And I mean, if you look at those phase meter, these are really sophisticated instruments, right? The second thing you need is you need to calculate those delay very accurately. And to calculate delay accurately, you need to know when you receive a signal here, at what time the signal has been emitted from this satellite. To do that, you need to measure the time of flight of the signal between these two satellites. And we do that with a sort of a house-made GPS. On a sideband of the laser, we beat a pseudocode exactly as the GPS does, right? So a sort of a Morse code signal. And when you receive, you do correlation with it. You know the pseudocode that they're receiving, and you shift the pseudocode. I don't know if you can see my hands. And you shift the pseudocode until they match. And when they match, you know that you get the right delay. And we calculate that we should be able to get accuracy in the measurement of the time propagation of the beam from one satellite to the other one with an accuracy of 1 centimeter here or 10 centimeter here, including clock uncertainty and all that. Innocenzo, should we have a break?
I see everything.
Say it again.
What?
Oops, I can't hear you. Yes.
I have some problems with the network, but I'm seeing noise analyzer.
Yeah, but should we have a break?
That it's working.
No. My question is, should we have a short break? I'm going in the second part of my talk. So if there are questions, or if you want to tell me something, we could have a 5-minute break
give people
with questions.
That's fine, yeah.
Okay.
Innocenzo, I think you have some problem with your connection because your connection is cut.
And what about mine, Nicole? Mine is okay?
Yes.
Okay.
Just a second.
Because my computer is very slow. Somehow Teams is slowing my computer, but that's okay. I'll manage.
No, it's okay.
Okay, so if there is any question, I would love to have a 5-minute break because that's a lot of material. For your information, this is basically midway to my final slide.
Okay, good. I don't see question, really.
I would like to first question.
Yes, please.
It is. I don't understand the distance between probe mass in LISA, 2 million of kilometers. It was what is the considerations which people decided this distance?
2 million kilometer?
Yes. Why 2 million kilometers? It is some prediction of possible gravitational signal or something else?
No, not at all. The reason is the following. I told you, let's see, we are at view graph 32. Let me see if I can show you. Yeah, I can. So I told you the signal is proportional to the length, to the dimension of the detector, right? This is the separation between the two spacecraft. So the larger, the better, right? Yes. But the larger, the better. But in reality, now let me go back to my slide. I will explain the slide later, but this is the response of LISA at high frequency. And you see it's getting worse. And why it's getting worse? The main reason why it's getting worse is that the light doesn't have, when the frequency of the wave is high, the light has no time to propagate across the detector in a cycle of the gravitational wave. And that suppresses your sensitivity to the gravitational wave, right? So that's one. So one is you can do big, big, and big, but you're paying a price at high frequency. And so you have to stop before you're paying your price at high frequency. There is a second reason. The farther away you go, the less light you collect. And the less light you collect, the more noise is your interferometer.
Yeah.
And so you have to make a compromise.
I see. Thank you.
So it's the biggest possible detector given those two constraints.
Okay. Thank you very much.
Sure, my pleasure. Any other question?
Yeah.
If you allow, I would ask the second question.
Please.
Please.
I cannot see your name because I don't see the participant.
Sergei Vitale.
Nice to meet you.
Yes. You tell about drag-free satellite. What is I understand that drag-free cannot be perfect. There is some noise. What is the level of noise which is?
You want to spoil some of my talk, but I can.
At the next part, yes.
No, but in reality, I don't have a graph on that one. I have too much stuff, and so So I will answer your question. It's basically tens of nanometers per root hertz. This is always per root hertz. I don't know if you're familiar with this concept of power spectral density, but basically it's the nanometer scale. That's what we can get. The reason is complex. It's a combination of factors, but I would say the dominating one is the noisy of those thrusters. Those rockets are not perfect. Actually, the rockets are just compressed nitrogen with a valve that we open, and so you get the recoil from the nitrogen which is expelled, and the valve that you open is not a great masterpiece of mechanical precision, and so that's noisy, but it's sufficient.
Yes.
Remember, it's mostly is a collision avoidance technique. In reality, it's not like that because there are force gradient that couples somehow the test mass to the spacecraft, but mostly is a collision avoidance thing. So in principle, provided you don't touch the test mass, you can do a loose job. It doesn't require very high precision.
And this accuracy is demonstrated in LISA Pathfinder.
Yes, absolutely. But
Excellent.
Now I'm not going to answer any question about LISA Pathfinder.
Thank you.
Otherwise, you spoil the rest of my talk.
Thank you very much.
Sure, my pleasure. So I would resume the talk. What do you think, Innocenzo?
Yes, if you want to it's 6 minutes to 5. Maybe, I don't know. Maybe we can give room for another question, maybe on the YouTube channel. Mikkel, do you see anyone raising his or her hands? Maybe not. Well, Stefano.
No, not at the moment, but there is a question now on Teams.
A question on what?
There is a question from the Teams chat. Okay, so
can you read it?
Yes. So it says it's by Yuxin Chen. Sorry for my pronunciation, which probably is not correct.
Nice to meet you, Yuxin.
Thank you, Professor. May I ask a question? The data of LISA is different from LIGO, where thousands of signals are simultaneously overlapped. But considering that LISA has not been launched, what can we do now on data processing?
A very good question. My guess is that, Yuxin, you must be young, so it's a very relevant question. So the people are working around the clock, I must say, to prepare for this data analysis. The data, you must realize that the data analysis is a gigantic fit with 100,000 parameters to the LISA data, right? Because you have to put in the data template for everything at once. That's not trivial at all. There are, I would say, hundreds and hundreds of physical review D and even physical review letters on the subject. And the people in the LISA consortium have working groups preparing data. One of the things we have to deliver to ESA in preparation for the LISA is a working pipeline that demonstrates on synthetic data, artificially produced data, that we are indeed able to extract the science from the data. We are more than 10 years from the launch of LISA. I would say that these 10 years are sufficient to work out this problem, right? Don't think that we can talk of this in 10 years from now when we get close to the launch. This is a very hot problem. And you're very welcome to check the literature and see all the work that has been done on that. Even more, you're very welcome to join the LISA consortium. I hope I answered. Okay.
They said thank you.
Sure. Shen. Okay, then what do you think? Should I resume?
Stefano, I think you can start over again. Okay.
Okay. So, the link is noisy. The link is this spacecraft sending a beam to another spacecraft and the receiving one measuring the frequency and correcting for the acceleration and having this gravitational wave signal. That's noisy. Noise is contributed by two things. You have to cancel this frequency noise that we do with this complicated time-delayed interferometry. Once you have canceled that, you're left with the sources of noise that cannot be canceled. The first one is exactly the acceleration of the test mass, right? I told you, it's like sending the beam directly from one test mass to the other one. So you're going to detect if the test mass accelerate one relative to the other one. Mind you, accelerated not because of the gravitational wave, accelerate because something is pushing them, thermal effect, magnetic effect, collision with molecules, and whatever, right? And the people calculate that at a low frequency, the sensitivity of LISA will be limited exactly by this phenomenon. By the way, this is the H sensitivity of LISA, I think you're familiar with this plot, is spectral density, so it's 1 per root hertz. For the people that are real theorists and hate those things, the spectral density of a noise process, you can think is proportional to the minimum monochromatic signal you can detect at that frequency for a given measurement time. So if you measure by 1 second, you take this number, and this number is the minimum amplitude of a perfectly monochromatic signal at that frequency that you measure, right? Just in case somebody is not familiar with it. Obviously, this acceleration of the test mass is not the only source of noise. You have to measure this damned frequency, and you do by interferometry. I'm not going into any detail. It's a heterodyne interferometry, and it's noisy, right? Even if the test masses are perfectly still and there is no gravitational wave whatsoever, you will see some noise at the output of your phase meter that measure the frequency of the wave, right? However, the people calculate that this is only going to set in at frequency above something like 10 millihertz. Now you must realize that the real reason to do LISA is low frequency, right? And so if you take the LISA science requirement document with a list of all the sources that LISA will detect, it's not surprising that most of the signal to noise ratio for the most important sources of LISA is accumulated where the noise is dominated by the acceleration of the test masses. And so the problem of the acceleration of the test masses has been the key instrumental problem, at least in the early day of LISA. So what is needed? What kind of acceleration is needed? I told you the satellite accelerates too much, but how much you can tolerate to accelerate? And this is a requirement. Again, a spectral density, right? And so if LISA has to deliver all its science, you must be below this black line. This is noise. So the lower, the better, right? The lowest, the better, right? So you must be below the black line. Now look at the scale. These are meters per second square, right? So the acceleration due to gravity is 10, right? So you're talking 10 to the minus 15 times the acceleration due to gravity. So this requirement is sub femto G. I like femto. It's like tera. It looks very fancy, right? So you need to have those two test masses accelerating one relative to the other because of spurious disturbance like magnetic or electric field less than femto G. There is no way you can demonstrate that this is possible in a ground laboratory because of 1G, right? Because of the acceleration of gravity. As soon as you move, you will have huge disturbances that will cover everything. It turned out that even if you try to do an experiment in low Earth orbit, like, your orders of magnitude away because of the gravitational gradient of the Earth that still produces a big gravitational field. And you must realize that LISA came to ESA at the end of the 1900s. And at that time, the only space mission that used free-falling test mass was the GEODESY, the very successful GEODESY mission called, GRACE, by NASA and DLR, which flew with big success. You see that the requirements in terms of acceleration, what is this? 8 orders of magnitude? And even the most sophisticated mission that has flown even later than LISA Pathfinder, but in low Earth orbit, like microscope. This is the equivalence principle test made by CNES in the last few years, cannot get to this low acceleration. So when we convinced ESA that gravitational wave astronomy was the name of the game for astronomy in the future, they said, yes, you convinced us, but is it going to work, right? How can we give you a couple of billions, because that's the cost of LISA, right, overall. Billion doesn't matter if it is dollar or euro on that scale, right? So can we trust 2 billion on something that you cannot possibly demonstrate on ground? And so please convince us. We are ready to give you millions to show us that it's possible, You have to have a very convincing case that this is possible. And fortunately, because disturbances, electric field, magnetic field, are generated mostly on board the spacecraft, you don't need those two test masses to be separated by 1 million kilometers. So you could do a meaningful test if you take out the telescope and all this thing here and put a second test mass in the same satellite, right? So you may say that you have taken the 2 million kilometer LISA arm and squeezed inside the same spacecraft. And we are talking alpha meter, 40 centimeter to be precise. So, and that's what LISA Pathfinder was. So very soon became, that was the proposal of the test. So it's two test masses in the same spacecraft, two interferometers, one measure the same way you do with two spacecraft, you measure the relative acceleration of the two test masses, and one interferometer measure the acceleration of the spacecraft relative to one of the two test masses, so that you can do drag-free relative of the spacecraft relative to this test mass. So this jitter here, to the colleague that asked me the question, is the 10 nanometer. Unfortunately, when you have two test masses in the same satellite, you cannot follow them along the same direction, right? Either you follow one or you follow the other one. And so in LISA Pathfinder, contrary to LISA and spoiling the test to some extent, we were forced to apply a little electrostatic force to avoid the second test mass drifting away from the other one and the satellite, which is following the first one. And this is a limitation of the test, and I'll tell you about the consequences. So if you want to see the hardware of this test, that's the hardware. So these are the test masses. Let me see. Oops. These are the test masses. Gold platinum, 5 centimeter. It's gold platinum. Why is gold platinum? Because it's very heavy and it's very non-magnetic. Because gold is diamagnetic and platinum is paramagnetic. You mix, you get almost zero. You get 10 to minus 5. They are very pure, homogeneous, and very heavy. And acceleration is force divided mass. And so the heaviest, the best. And then you have an optical bench, which is hosting all the interferometry, and is made with the same technique of zero Dürr. I'll tell you a bit more about that, how you attach optical component to this zero Dürr. It's zero Dürr, which is a glass ceramic, because it's very, very stable, right? And then you start having a lot of accessories. You have the electrodes that I told you why you need the electrodes. And in LISA Pathfinder, you also need the electrodes for this extra force you have to apply, but it's the same set of electrodes. It's the same equipment we have to apply on LISA. You have to carry, this test mass has no grounding wire, right? So there is no connection to electrical ground. So it keeps charging up because of cosmic ray. And how you discharge it? And you discharge it by shining UV photons all over the place. I'll tell you a bit more later. And you generate photoelectrons that neutralize the test mass. So you have to carry UV light and all the accessories. You need a caging mechanism. What is a caging mechanism? If you launch this test mass with millimeter space all around, during the vibration of the launch, this is what the sailor call a loose cannon, right? A cannon that can move freely in the ship and would hold the side of your ship, right? This would destroy everything. So you have to lock the test mass with a mechanism with almost 1 ton force on the test mass. And then when you are in orbit, you have to release with enormous precision to orbit. So a rather sophisticated mechanism. And then, believe it or not, despite you flying in vacuum, you have to enclose everything into a vacuum enclosure, because you have to do the vacuum on ground to test things. And then we'll vent, this vacuum enclosure gets vented to space once you are in orbit. And if you want to see, this big complement here went into the center cylinder of a dedicated satellite. There was no other instrument on LISA Pathfinder, right? And then I'll tell you what happened on the satellite. But a few pictures on the real hardware. You already saw the test mass and the electrode housing. When you complete with all the accessory, maybe you recognize a few details, the caging mechanism, the entry for the UV light and other things. And assembling this thing is an optical job, because this test mass, remember, is the end mirror of an optical system. So it needs to get aligned to micron accuracy and sub-millirad accuracy that industry did with extreme success. This was really goes to unperishable credit to European aerospace industry. The optical bench is another masterpiece. You see, these are zero-dur mirrors or beam splitter glued to a zero-dur base plate. The way you glue this thing is the same of my colleague in Virgo, is the same technique my colleague in Virgo and Ligo used to glue the mirrors to the fibers that suspend the mirrors. It's the silica bonding, right? Now here, however, you're aligning optical components. So you have to align this component, put a little sodium hydroxide between the plate and the component, and you got 10 minutes or less to align these things to submicron and submillirad, and then it freezes, and the mechanical and optical properties are like you had machined this thing out of a piece of bulk. And it was successful. The alignment was marvelous. And so you see here the optical bench once was integrated. And so, as I told you, this is the assembly of two things with the optical bench. The two test masses with all their accessory 20 kilos each are kept together by glass to get good stability. Look at the complexity. As an old ground-based experimentalist, if you had showed me this picture in the old days, I would say, this is not going to work. It's too complex. And so it shows you what the people in the space sector can do. They can do such complex instruments that you turn on and they work, and I'll tell you. And so you see the tank going into the central cylinder, and here you see the central cylinder being hosted in the satellite being assembled on the propulsion module that we needed to reach our final orbit, and being put in the fairing of one of the Ariane space launcher, Vega. This is made it's manufactured in Italy, it's an Italian design. And then we launched it in December 2015, and we cruised for a month to reach our final orbit, which is a Lissajous orbit around what is called the Lagrange point number 1 of the Sun-Earth system. You know, this point where the pull of the Earth compensates a little bit the gravity of the Sun, so that the satellite here would go around the Sun at the same speed of the Earth. So it's like having it on the top of a pole, which is very handy to communicate with the satellite and to have the satellite taking the light from the Sun at all times. So it took us roughly a month to start turning on instruments. So believe me, I spent 15 years preparing LISA Pathfinder. So turning on the instrument and seeing that they all turned on and worked has been one of the topical moments of my life. We separated the propulsion module that we needed to reach the final orbit. And on February 3, we made another big event with decaging. We unblocked this blocking mechanism. And we had no guarantee, this has never been done, that the test mass didn't stick to the caging mechanism. This is an animation of how things went. Right, you see probably in a second the test mass here, it detached. It didn't go very well the first time, but we learned how to do. And here is the trace of the X coordinate of the test mass as sensed by the electrode, not by the laser, hitting maybe a little bit aside and then being captured by an electrostatic control loop. So this was even more critical than the launch itself. So you would not be surprised if my project manager, which is the guy with the orange sweater, which is a very, very cool-blooded Spanish colleague who never screams and laughs, was really happy, because this, you know, if you do not decage, there is no mission. And that's true for LISA too. So a very topical moment. Okay, so we got a machine and what we did with this machine. So before I tell you what we did with this machine, let me tell you what we were requested to do. So these are the same plot. This is the same plot with different color that I showed before. These are the LISA requirements. So if you want LISA to work, the test mass should not have acceleration in excess of the yellow line. So you should be here, outside the gray area. At lowest frequency, we don't care. At higher frequency, we don't care. In this frequency range, that should be it, right? LISA said, well, look, I don't want to spend a fortune on that. So as a standard practice in engineering, if you can show me that you can get within a factor 10 from the LISA requirement, limited by your test bench, right? So 10 times more noisy. Remember, up is more noisy. And if you can show me this from a millihertz on, right, I would levy this part here, and I would not require you to do ground testing at below 1 millihertz that are very expensive because it's days and days of testing. So we were required to be not outside the gray area, but outside the blue area. Okay, so we worked to that, and we obviously had a noise model. And LISA Pathfinder noise model is a book of 276 pages because the name of the game here is you need to think everything, right? And so you don't have the luxury that somebody comes in your lab and say, have you thought of this effect, right? So we are many experienced physicists, and so we try to think everything. And the list of everything, including things that are not relevant, is 276 pages. However, there are 10 top entries, and the 3 top entries we were expecting to limit the sensitivity were the following. The first one is exactly the fact that, contrary to LISA, we had to apply a force to one of the test masses to keep it in the satellite, right? Because we could follow only the other one. You apply a force electrostatically, and you generate electric field with a voltage generator, and voltage generator are noisy. And it turns that for a given voltage generator, the more force you want to apply, the more noise you do, right? For a given volt per root hertz, you do more Newton per root hertz if you want to apply a force whose peak value is very large. Actually, the way we do the thing, this depends even on a setting. You prepare the system to counteract the force of so many newtons, and the larger the setting is, the larger will be your force noise. This frequency range here, you see, this is the crossing between a flat contribution and this 1 over f squared contribution due to this electrostatic noise. This flat contribution here is Brownian noise. This is a fundamental phenomenon at thermodynamic equilibrium. Wherever you have dissipation, you have fluctuation that you can calculate. And this is due to the collision of the test mass with residual gas. Our goal was to achieve 10 micropascal pressure, millibar pressures, right? And with those pressure, we were expecting to limit it at this point here, at this level here, right? And then at a higher frequency, this is not real acceleration of the test mass. This is the fact that you're measuring the relative acceleration with an interferometer. The interferometer is noisy. Usually they are white in displacement. You measure so many meter per root hertz. And if you convert the displacement into an acceleration, you have to do a second derivative. So you multiply by a frequency square, and you have this characteristic razor that accompany all performance plot of all interferometer all around the world and in all. And so we didn't need such a sensitive interferometer, 10 picometer per root hertz, but because we flew the first interferometer in space, we tried to achieve the same LISA, the same sensitivity of the local interferometer in LISA, okay? And so we went into operation on March 1st, and bang, we are on the prediction. So we were better than requirement as expected, and but even more striking, we were at the prediction where it matters at the low frequency, which is the surprise of the field. You can calculate this experiment build them on ground without testing them, except for partial tests, fly them, and they behave as you were expecting, right? Which was a big surprise. There's one place where they did not behave like we were expecting, which is here, where the interferometer behaved much better than what we could demonstrate on ground. On ground, we had demonstrated the picometer, but the interferometer showed femtometer, tens of femtometer per root Hertz sensitivity, and the noise of the interferometer, we explain it within a factor 2. So we can account for the noise we see of the interferometer. This was not the case at all when we tested this on ground, because at this frequency, ground testing is miserable. The noise of the bench is really miserable. But we could demonstrate the 10 picometer, which was enough to fly the mission. So why we had, so I told you, at low frequency, we were dominated by the fact that we had to apply a force. And why the heck we had to apply the force? Well, the reason is the following. Is the gravitational pull. This is 20 kilos, and the optical bench is 10 kilos, I think, and this 30 kilos pull this test mass. And so you can follow this test mass with your satellite, but this will be pulled and will accelerate and hit the walls of the electrode house. So how we cope with that? You can compensate with an electric field, but you need a huge field, and this will be too noisy. So we took a two-step approach. We calculated the gravitational field. That's an easy thing to say, but it means that all the provider of all equipment in the mission had to weight their component and to measure the position of the component to a certain accuracy in order that we were able to calculate the gravitational field. Then we machined a tungsten compensation mass. Tungsten is almost as heavy, it's one of the heaviest things you can do, and put a compensation mass that was intended to balance the gravitational field of this. That's a risky thing, right? Because if you get it wrong and you put it in the wrong place, you may produce more field than the one you're trying to compensate. And so the name of the game here is, how good were you in calculating this gravitational field, right? And so we had to make an exercise on errors. What is the maximum error we have in the position of this element down to screw level, right? And what is the error on the mass? And the conclusion was that we should have been able to guarantee that the residual force was a fraction of a nano. It's a picometer per second squared. The mass is 2 kilos, so it's basically a nanonewton. We compensated to 0, but the final uncertainty was such that you could have a +1 nanonewton force or a minus nanonewton force. And so you had to be prepared to compensate that force. But when we went up, we discovered that instead of doing 650 of those units, we have done 25. Again, industry and a little bit of luck have done this work so well that we had compensated much, much better. So we could decrease the setting of this maximum force needed to keep the test mass with the satellite. And so as soon as we went to this 50, instead of 650 to 50, the noise at low frequency decreased as expected, or almost as expected. Notice that in the meanwhile, even the plateau here, due to the Brownian noise, the collision with the gas, had gone down. That's not to our credit. The reason for this is that the vacuum enclosure that surrounds the test mass is vented to space. And so the pressure inside around the test mass kept going down, like in any pumping system in your lab, right? And actually, if you plot this level here as a function of time, you have a plot which seems to taken from one of these vacuum handbooks, right? Where so you can interchange Brownian noise with pressure, because the Brownian noise is proportional to pressure, and everything looks like we are seeing the pressure generated by outgassing of water around the test mass, as you expect in a vacuum system like this one, which is a pretty complex vacuum system full of components. And so by the end of the mission, we had gone even farther. Something had improved also here. And so by the end of the mission, we were so much better than I'll tell you what was the political consequence of this performance, that you may see the blue line is better than the LISA requirement with margin, as Innocenzo anticipated with the spoiler, than what LISA requires. Now, LISA Pathfinder was not just that. We made many experiments. We are about 20 papers out of the data of LISA Pathfinder. And I'll give you a flavor of those experiments. For instance, the charging. We had simulated with these high energy tools, Giant4, Fluka, what would have been the charging of the test mass. The charging is due to the fact that cosmic ray muons hit the satellite, generate showers of secondary protons, and this hit the test mass and charge the test mass. What's the problem? The problem is that these are random events. So you have a charge that builds up on your test mass at random, right? Like a staircase, right? And if you have any stray parasitic voltage across the test mass, the difference of voltage times the charge is a force. And so you will have a staircase force disturbing your test mass. And the calculation with the Fluke and Giant said, yes, it's going to be Poissonian. You will have a Poissonian rate. So expect this force, if you do the calculation, if you're familiar with this thing, expect a 1 over F noise, forced noise, if you have any parasitic voltage. And unfortunately, in metal system, you have parasitic voltage that are not under your control, because the work function of metal changes from place to place, but this is another talk of another 2 hours. So we went up and we were able to measure the charge of the test mass. How we did? Well, the same way it spoils your performance. Instead of having a DC voltage, we applied on purpose an oscillating voltage so that we had if you have a charge on the test mass, you see an oscillating force. And if there is an oscillating force, the test mass will move and you will measure the acceleration. And so that's what we did. And so at frequency well below the frequency of this thing here, that was 10 millihertz, we could trace the charge on the test mass, which is this noisy curve here. And believe it or not, if you do the spectrum, it's exactly 1 over F. The rate at which these charges arrive was within a factor 2 of our simulation with the GN4 simulation. That's not because the calculation were wrong or the model was wrong. Is that we also have a contribution of low energy electrons, and those are not taken into account by GN4. More important, we could show that if we increase the voltage drop around the test mass on purpose with a DC voltage supplier, we see a lot of noise. But on the other end, we can compensate the voltage to balance any parasitic voltage you find, and you always find 100 millivolt of parasitic voltage. You apply a minus 100 millivolt, and the noise goes into what you get when the test mass is completely discharged. So this was a big success. The discharging we did with UV light. I'm not sure I want to go into that. We discharge by sending UV light either here, so that we generate electron here that go to neutralize the test mass if it is positive, or we extract electron from the test mass so that we make it negative. And we made an extensive testing campaign where we show that we can get whatever voltage you want with whatever illumination. So this was a very practical instrument that we used continuously to keep the voltage of the test mass where it should be, not to increase the noise. There is another interesting experiment that's maybe for the connoisseur. I told you that we had to apply this electrostatic force. So, and because we applied this electrostatic force, we corrected the data, right? Because if you don't correct the data, you're fooling yourself. So if you take the relative acceleration of the two test masses without taking into account that you have applied this force here, you measured 0, right? If this feedback is very good, you measured 0. So what you do is that you measure the acceleration, subtract the force you have applied, and that's the force that has been applied by third parties, as a lawyer would say, which is what you're interested in. But is that is that right? Are you cheating? You're subtracting strange things. Are you sure that this is the right thing to do? Well, we had compensated gravitation so well that we could let the test mass free for a while. So we could do an experiment where we cut the electrostatic suspension for 300 seconds. In this 300 seconds, the test mass started to drift in one direction, we kicked the test mass opposite to the force, which was gravitational, to which it was subject. So the test mass started to go in one direction, slow down because of gravitation, start to accelerate in the other direction. And when was hitting some comfort zone, boom, another kick. And the kick of force are given here. Now, the noise from third party is independent of what you do here, right? So in between those kicks, there is no other noise. And because this is a very low frequency noise, you can interpolate the noise trace you have measured, cutting out these gaps where you have applied a strong signal. And that's what we did. And what we got is that the excess acceleration noise we measure one way is the same as we measure the other way. This is, we were prepared to do that anyway, to try to put an upper limit to the noise due to the electrostatic actuation, but the compensation was so good that this second method that was expected to be a bit more noisy was in reality as noisy as the standard method. So a lot of fun, I should tell you, and a lot of reassurance that we were not cheating ourselves. Well, this maybe I can skip because of this very accurate drag-free. We could detect immediately if the spacecraft was hit in a macrometeorite because it accelerated relative to the reference test mass. And so we could see the acceleration of the spacecraft relative to the test mass. It turns that we had quite a statistic of micrometeoroid hitting the test mass. Notice that in the differential acceleration, we don't see anything because the system is very much isolated. So we see that the spacecraft is being hit. Well, we got two examples where it hit so hard that the spacecraft went into space mode, in safe mode. But beside that, and don't ask me a question on this plot, but the reason why I'm showing is that we even published a paper on the statistics of micrometeoroid around L1, which was well received by the community of micrometeoroid, believe it or not. So let me go toward the end. Just give me 1 minute to tell you we did much better than we expected. And do we understand what we got now? I told you we predicted the experiment very well, but then we improved. And do we understand what is left? So this is just the noise at the very low frequency where it's matter, right? Above a certain frequency is the Brownian noise, so you can play this data analysis trick and subtract the the Brownian noise. So that's what remains, is the red line. Do we understand it? Is our model of the disturbances enough to understand this excess over the Brownian noise? Well, maybe. This is a long work. It's going on since years. We're probably achieving some semi-final results. I'm not authorized to publish it, so I put a big work in progress on it so that you don't take it too literally. But if we account for all we know, with also some sophisticated data analysis technique, at deep in the LISA band, we basically understand everything, which is important because we are confident we can reproduce it. And we probably understand things within a factor 2 at the lower frequency. But there are still some tests and experiment and simulation that we can do. This excess is very stable. To show you how stable I have to cook it a little bit. You see, this is almost perfectly 1 over f. So if you multiply by the frequency, it becomes almost a constant, right? And I can take the average of this constant. And what I'm showing you here is this constant as a function of time. These are different noise measurement run. These are hundreds of days. So this is 1.5 day of mission. And you see, look, I'm speaking to the experimentalists. You usually show noise in a logarithmic scale because fluctuation and variation are very large. To give you a feeling of the stability of this instrument, this is a linear scale. This is a linear scale. So this noise fluctuated by no more than, say, 20% over 1.5 years of mission. And so this is also very reassuring for LISA, though some theorists would like to have more precision in the noise because they need it in some of their calculations. You want to see this noise compared to the acceleration or the equivalent acceleration due to a black hole signal. So this is a simulated acceleration of test mass due to my red black hole signal, and the red line is the noise of LISA Pathfinder. I say noise? I don't see any noise. Well, if you zoom in, you see the noise, right? Now you realize why when we show this to ESA, ESA said, okay, let's go for LISA, right? And now 4 years ago, almost exactly 4 years ago, ESA decided to start working, finally working to LISA. So we are in what is called the phase A, or formulation phase. And so don't ask me about the launch date, because those are highly unpredictable. Our next milestone to which we are working full steam, a lot of people, is mission adoption, which is when the space agencies say, okay, the design is convincing, the technology is under control, let's spend the big money and build a satellite and move toward the launch, right? And we aim and doing this in 2024. We have 2 competing industrial studies of design, and the result of this fact is that I cannot show you anything because it's all secret, because one industry should not see what the other industries achieved. But I can tell you, LISA is a very solid concept. It didn't change. You may change the shape of the spacecraft, but it's 3 spacecraft launched by the same launcher into this orbit. Here you can see some shadow engineering we are doing in the consortium, and you may see the telescope and the optical bench and the test mass with accessory, together with the supporting structure and all. This is the vacuum duct to evacuate the things. This is a piece of electronic and so on. We are working to the ground segment. That's an answer to Yi-Chin. That was your name. So for instance, this is a block scheme. You're not supposed to read it, but just to be impressed by the complexity of the block scheme of the data reduction to go from this 6 frequency measurement to a gravitational wave signal. And we're working to the technology. For instance, this video here that I hope you can see shows how the optical bench of LISA Pathfinder was assembled. So this time lapse shows these poor colleagues of mine putting one thing, measuring alignment with the laser, all this in 10 minutes. Now, this was the simple optical bench of LISA Pathfinder. The optical bench of LISA has many components, so no way you can do this by hand, how skilled these colleagues are. So one of the technology is a robotized, computer-controlled fabrication line for the optical bench, associated with a coordinate machine to measure all the coordinate system of this device. But there are other technologies that are more mundane. You have to compare the measurement of 2 joining arms in the same satellite. You cannot do by sending a laser from here to here, because these are moving. So you have to connect this with the fibers, and this fiber must be as quiet and as silent as free propagating beams. That's not a trivial it's not a trivial interferometry issue, but there has been very good progress. We are very confident that we will be at this TRL6 before adoption. There is a lot of technology development in the United States, the telescope, the laser, the charge management device, because the sharing of responsibility is that ESA is the lead of everything, but NASA is contributing, as I say, the telescope, the laser, and the UV light source for the discharging. The GRS is provided is a team of Italy, which is leading the team, Switzerland and the US, and the other component is a team all across Europe, UK, Germany, France, Spain play big roles, but we have Belgium, Denmark, the Netherlands, the Czech Republic, and other actors are joining, and we probably will have also contribution from JAXA, the Japanese space agency. And if you want to see the kind of number of scientists that are working in various incarnation to LISA, mostly to the theory and the data analysis, again, to pick up the question by Nishin, you see here the true international composition of this fantastic team of close to 1,500 people. And that was my last view graph. No, sorry. I thought that that's the third time I do this. Maybe you want to know, is there any other thing in space besides LISA? Well, you must know that there are two efforts in China, one for a LISA-like from the CAS, the Chinese Academy of Science, it's called Taiji, and another one from the Sun Yat-sen University and the Wuhan University for a geocentric LISA-like experiment. Probably China will do only one of those two to be decided, and both teams are working very hard to improve their space abilities. They both have flown some small demonstrator technology. Final, I'm sure that's my final view graph. ESA has run recently an exercise that they do periodically, what we are going to do after LISA, what are going to do in the 2050 time frame, not my time frame, you realize? And at the end of a very hard and very thorough work, one of the recommendations is that ESA, depending on the status of the knowledge at that time, should decide if flying either a successor of Planck or a successor of LISA. And in the range of successor of LISA, the two most interesting things are going at a higher frequency relative to LISA, filling the gap between LISA and the ground-based detector, where there is a lot of signs of this intermediate mass black holes and other things. But there is the possibility of having a much larger LISA, putting spacecraft in much larger orbit and going at frequency even below that of LISA, or achieve improved sensitivity at lower frequency. This is not going to be decided anytime soon, but this is now solid in the ESA plans, and so there will be study for LISA successors in the next decades or so. And now I promise this was my last view graph, and let me thank you for your attention. And I always finish my talk by thanking this group of colleagues that made the LISA Pathfinder, and it was such a privilege to serve with them. Thank you. Done.
Thank you very much.
Thank you very much, Stefano.
Very nice.
Wonderful lecture. Wonderful lecture.
Really wonderful.
Thank you.
Please, comments.
Questions?
So, room for questions.
Should I stop sharing so that I can see the faces? I don't know.
As you want.
Let's see, now you see my... Oops, did I stop sharing? I stopped.
Yes.
So in case I need, I will share, okay?
Yeah.
In case I need the view.
Okay.
Questions? Comments?
If you want to put questions, please raise your hand.
Take your time, don't be intimidated.
No.
It's a lot of things, right? So the people at the end say, question on what? Pick one.
Well, while the people think about that.
It's Sergei Vichanin. I have one question. I don't know how to raise hand.
The question is, how do I raise hand?
Yes.
Sorry.
The question is very simple. The LISA Pathfinder was the first approximation of LISA. Does it plan the second approximation, or it will be just collection of LISA interferometer in space?
No, there will be no other precursor. There is a ground-based development, but we go for LISA.
Okay. Thank you very much.
Too expensive to do any other thing.
Stefano, what is the expected lifetime of the experiment? Also in view of the fact that in order to achieve, collect, and manage all the information, for instance, on the galaxy, a lot of time will be required. So what is the expected time span of the experiment as a whole?
Okay, good, very good question. The way it is now, the nominal mission is 4 years, with possibility of extending to 10 years. 10 years is limited by the stability of the orbit. I told you that the orbit is a solution of the Sun and the Earth, actually the Sun and Lisa. No? The presence of the Earth, the other planets, makes the orbit in reality a drifting orbit. And so after 10 years, you would need a maneuver, and the maneuver is impossible because you have to carry the propellant with you, and that's right. However, the people are asking, and the science team of LISA is working toward extending the nominal mission to 6 years, and the extension to 4, because they say we want the 6 years. However, the galactic, it's already impressive. The galactic binary resolution is already impressive with 2 years because of the integration time. No, can't hear you anymore. You're muted.
Any possibility that the actual lifetime of the experiment may be longer than the expected one, as it happened, for instance, with Chandra and other objects? In that case, you don't have the problems related to keeping the configuration, of course. But is there any chance?
So you know what happens with this orbit is that because it's a drift away orbit. Can you hear me? You come and go. So this is a drift away orbit. So many things happen. The velocity, the relative velocity of the spacecraft become big, which give a lot of Doppler and stresses the interferometer. But also the communication to the satellite becomes more and more difficult because the distance to the Earth keep increasing, right? Mm-hmm. In terms of consumable, we have a main consumable, which is the nitrogen gas we use for the thrusters. However, all studies say that we should have plenty. We could go well beyond the 10 years. However, one consequence of that is that maybe we will reduce the mass of the nitrogen gas on board more than. So I would say no. The hopes that it goes beyond the 10 years. Unless somebody finds some very clever trick without any propellant.
It's difficult.
It's difficult. We launch another one, right? That's the best approach, is to launch another one.
Are there any other questions?
There is an end, F, erases this end, or her end.
Yes, can you hear me?
Yes,
I think there is a.
Yes.
Yes, of course.
Fabrizio Giovanni is my name. Sorry, I don't know why it was just F. I have like a naive question. Like, is the interferometer going to be full time in observing mode? Yes.
Yes. Okay.
Or is it going to be like with the ground-based detector, that there are periods in observing runs and other periods when the interferometers are not observing?
No, the baseline is that you turn on LISA and you observe. However, there are maintenance operation that needs to be carried. One is the rotation of the antenna toward the Earth. During this operation, it seems that we do not interrupt operation, but you're going to pay a price in terms of quality of the data. However, ESA wants a requirement, and so for the duty cycle, in case you have accident, right? Or you predict that some equipment may fail, and the current duty cycle is foreseen to be 75%. but all these numbers are the subject of the study, and I'm optimistic that the needed duty cycle will be in excess of 90%, because those operations of turning the antenna, we're talking a day or so, right? Or discharging the test mass, it's a day or so, and so you will have a day every 2 weeks, every fortnight. We also will have protected periods. If we see an event coming, like the coalescence of supermassive black hole, we can predict months in advance. And so we can say, okay, from that date to that date, you shouldn't be doing any maintenance, because we want to follow the collapse in detail. Right?
Oh, thank you. Thank you. I didn't think about that. Thank you very much.
Sure. Good question.
More questions? I'm trying to see whether there is any raised hand.
GS has raised his hand.
Giuseppe. Giuseppe,
Hello?
please go ahead.
Okay, can
Yeah?
you hear me? Okay.
Yes, I can.
Yes.
I just wanted to ask something about the sky coverage of LISA. What is it will be able to cover all the sky, or it will have some regions, like for instance we see with Ligo, Virgo?
No, it covers everything, because it's 3-arm and it's rotating around the sun, and basically there is no blind spot. It's basically covering everything, so it's basically omnidirectional. I think ET should have the same property, huh?
Yeah, I sent this.
Yeah.
Oh, okay, thank you.
Don't hesitate to make questions, and I address these especially to the students who might be shy in posing questions. There is no reason to be shy when it comes to
remember
science.
that many years ago I was a student.
Me too.
We
I
were
think
a student. We have been there. We know how it feels.
Lillo.
Hello. I have a question just about the difference or the decision to go in the space or under the Earth, like an Einstein telescope. What is the differences? What are the differences? And why we should prefer a way or another way? I don't know.
Yeah, no, I understand the question. Going underground suppresses a little bit the gravitational loss. So if on surface you get 10 hertz, underground you get maybe 5 hertz. But here we're talking 20 microhertz, that you can forget, right? A millihertz you can forget, right? The hertz is too noisy, even if you go in the center, which I would not recommend. I don't think. So no one has come with any, I've seen studies of active feedback system to be demonstrated that may claim 0.1 hertz. I've never seen anything below 0.1 hertz, but also, I mean, if you go to real studies like ET, Cosmic Explorer, even 1 hertz is not for the next generation, which is not unthinkable. 1 hertz, I don't think is unthinkable, but it's not for the next generation. And the way it's not unthinkable, you should ask to Jan Arms, right? It's to correct for the gravitational noise by measuring the motion of the Earth's surface and having a model of the gravitational field, which is a technique that can suppress things by what? Factor 10 maybe, if you could, right? And you have to believe that. So there are no basic alternative. I think there's never been any discussion on that.
Thank you.
Sure.
Did anybody prepare some more questions or comments for Professor Vitale? Folks, last chance.
Oh, you can drop me an email. If you have a burning question, you can't sleep tonight, drop me an email.
I would like to make just...
I'm not going to answer. Sorry, no thanks. Go ahead.
No, I was just going to make a comment. The comment is especially for the benefit of our younger colleagues and the many students that are attending this beautiful lecture. You gave a practical demonstration about the fact that success in science is a number of ingredients.
We have lost you for 10 seconds in a sense. So success in...
A number of ingredients. One of the ingredients is talent. The other ones are patience and commitment.
And resilience.
Yes, and resilience. You are perfectly right. And I think that you as a person are an example of this. And I think that, no, I think that this is what I said also about Ray in the first lecture. I think that meeting these people who essentially decided to spend a substantial part of their life in these things, this is education in the highest sense.
Thank you. May I comment your comment? You freeze. You should know that I was prepared to failure. I mean, in the darkest day, we went very close to cancellation twice with LISA Pathfinder because we incurred in serious delays because of technical reasons. And there's been a time where LISA Pathfinder was a curse. So the advice of a wise person in ESA to a young person was stay away from LISA Pathfinder, right? However, this was a magic moment. There was no bandwagon. We were a group of people of believer and friends alone in Fort Apache, right? Nobody wanted to, steal LISA Pathfinder from us. They say, LISA Pathfinder. And I think I'm one of the most lucky person on the earth because a privilege like that, there is no money can buy it. It's sheer luck, right? So you fight. There are moments where you think, okay, I'm prepared to fail. I retire. I'll keep very quiet. People will forget me, and I have a garden, no problem, right? You have to prepare to that because you can fail, right? And I think may fail, right? But
it's not only luck; it's also courage.
Assisted luck, I call it.
Assisted luck.
It's assisted luck. However, I can tell
exactly describing what resilience means.
There is no shot of cocaine or heroin or whatever chemistry that can replace what I felt when we took the first data. I had to go home. So we were in Darmstadt, and I took a plane that my colleagues were processing the March 1st run, right? And I was in the room when the first processing went on, and it was very bad. And that's what I was prepared, that it was bad and we should have started to play with the machine. And then I landed in Verona, which is my hub, right? Went to the car and got on the telephone a message, a WhatsApp with a plot. And the plot is the plot that I showed you of the March 1st thing, no one else can feel what I felt.
It's what in the Zen philosophy they call the Satori. It's exactly that.
I mean, fantastic, fantastic. So you can live with frustration. You cannot live with regret. I don't regret anything.
Why?
But it's a good comment. Yours is a good comment. You need to be resilient and you need to be long-lived.
Yeah.
Brilliant.
Thank you, Professor.
Thank you very much.
Thank you very much.
Eating for your dreams helps for a long life.
Yeah, that's maybe. Okay.
Bye-bye.
I've been a pleasure.
Grazie,
Ciao,
Stefano.
grazie a voi.
Folks, I think this is the.
Bellissima.
Ciao, ciao.
Yes.
Ciao
Sì,
Stefano, grazie.
veramente molto bella. Stefano, io spero che also the students, and let's hope that this can continue into different directions. Maybe going into deeper details on some specific topics. Okay.
Next in presence, we hope.
Yeah, hopefully. Hopefully, yes. Stefano, ti ringrazio